its applications. It's my great pleasure to welcome you to the fourth and final for this year Math Matters public lecture. Our lecturer tonight will be Professor Thomas Hales. Many Minnesota alumni have become devoted regular attendees of the Math Matter series, so I'm delighted to acknowledge the support of ITAS, the Institute for Technology Alumni Association, which is helping to support tonight's lecture. Thomas Callister Hales was born in 1958 in San Antonio, Texas, and he grew up in Utah. He studied math and engineering at Stanford and then got his PhD from Princeton in 1986 under the legendary Robert Langlands. He did a postdoctoral year at the Mathematical Sciences Research Institute in Berkeley, was a member of the Institute of Advanced Studies at Princeton, and then was on the faculty of Harvard, University of Chicago, and then for 8 years the University of Michigan. In 2001, he moved to the University of Pittsburgh, where he's Mellon Professor of Mathematics. Thomas Hales is the sort of mathematician that I admire an incredible amount. He's a fantastic researcher and an excellent teacher and expositor. In 1998, the University of Michigan awarded him their Excellence in Teaching Award. That was the same year that he solved the 400-year-old Keller conjecture, and finished solving it in a marathon effort. The next year, Michigan honored him again, this time with the Henry Russell Award for Excellence in Research. Hales' computer-assisted proof of the Keller conjecture was so big and so innovative that now, 7 years later, the math world is still struggling with it. The prestigious Annals of Mathematics assigned a panel of 12 experts to review it. Now, almost 7 years later, they're about to publish part of the proof, the theoretical part of the proof, and what the computer section of the proof is going to appear in a different journal. The proof and its implications for philosophy and for the future of mathematics have been the subject of lots of writing and reporting in outlets such as Science and Nature, the New York Times. Hales himself is the hero of a very readable book I commend to you by George Spiros entitled Kepler's Conjecture: How Some of the Greatest Minds in History Helped Solve One of the Oldest Math Problems in the World. Having toppled a 400-year-old conjecture and continuing to challenge our notions of how to carry out mathematics, Hales might have rested on his laurels, but he has not. Amazingly, since proving the Kepler conjecture, he's proved two other venerable conjectures in geometry: the ancient honeycomb conjecture and the 60-year-old dodecahedral conjecture. Hales was the Euler Lecturer in Berlin in 2000, the Mathematical Association of America's Battles Lecturer in 2002, the recipient of the Chauvenet Prize for Expository Writing for his articles Cannonballs and Honeycombs in 2003, and the recipient of the R.E. Moore Prize for Applications of Interval Analysis in 2004. Now, in 2005, I'm very pleased to introduce him as the Math Matters public lecturer for tonight's lecture.
Thank you very much. I'd like to talk a bit tonight about computers and the future of mathematical proof. As we all know, computers have bugs. They make mistakes. They give us viruses and frustrate many of us every day of our lives. On the other hand, mathematical proof is something that strives to be free of all imperfection. I'd like to talk a bit tonight about how it is that these imperfect computing devices we call computers are so vital for the future of mathematics. Let me start with a few examples of computer glitches. In 1996, around tax season, a mail truck pulled up in front of a dentist office in San Diego to deliver some tax forms. Because of a glitch, there wasn't just a single tax form, but a stack 5 feet high of tax forms, not just one stack, but 40 stacks. And in the end, over 16,000 tax forms were delivered to the same dentist in San Diego. How did this happen? Well, apparently the software had a glitch that caused a repeating loop if you entered the abbreviation for suite as STE instead of SU and had a spelling error in the previous line. And this is exactly what the dentist did, and as a result got the 16,000 tax forms. So Chuck Barr received a library fine for $40 trillion in 2001. He was interviewed afterwards and asked how he felt about this. And, well, his response was, "It sure makes the heating bill seem small." Of course, the local politicians were quite happy about this and had plans for the expansion of the hospital in the local community. How did this glitch occur? Well, in this case, the barcode was read in for the size of the fine, and he was asked to pay the barcode in dollars. So these bugs were eventually corrected and were not so severe, but other bugs in computer programs can cost hundreds of millions of dollars. A very famous example is the Intel Pentium chip division error, which eventually cost Intel over $500 million to correct. Another famous example is the explosion of the Ariane 5 rocket, which again was a mistake that cost hundreds of millions of dollars. So in computer software, glitches are called bugs. This is a term that goes at least back to Edison, of a term for used when there are problems in a system. Typically, the instructions to the computer are written out as a series of statements, and as people are typing in the statements, on average, a computer programmer makes 1.5 mistakes per line as the computer code is being typed in. Of course, most of these are just spelling errors and small mistakes and corrected right away. But by the time the computer code is ready to be released to the public, there's still maybe 1 bug per 100 statements in the computer code. And this means that in, say, a typical cell phone, there would still be 600 bugs. One thing that surprised me when I looked at some software testing books, so there's an occupation of software testing where the job is to get rid of all the bugs and glitches from the computer code. One thing that surprised me when I first looked at the books on this subject is that the software testers do not even try to get rid of the bugs. In fact, this is a very important point early in the books, that you do not, as a software tester, you do not try to get rid of all the bugs. And even if you know where the bugs are and how to fix the bugs, you still don't fix the bugs in the computer program, unless you know that there's, first of all, some financial motive to fix them. And second, it shouldn't be too close to the release date for the software, because in fixing a small bug, there's always a danger of introducing a big bug and making things worse rather than better. So it's best often just to leave the problem alone. One example in one of the books, for instance, was a software program that when you moved the mouse in a certain way, it randomly deleted paragraphs in your word processing program. And this tester concluded that this was not a bug that was serious enough to fix. So if any of you have had this problem, Don't ask anybody to fix it. It's there by intention. Okay. So one question we can ask is whether it's really the fault of the computer or the fault of man that computers are so full of bugs. And I just want to read what a researcher at Microsoft UK has said, that our experience with computers is that given a consistent set of instructions, they compute consistently. It's just hard to give them a consistent set. So from this view, the problem is really more with human error than the problem of machines. So now I want to leave the realm of computers behind for a moment and enter the realm of mathematics. So people say, by contrast, that mathematics is perfect and free of any kind of imperfection. And this is the type of example we might see for the perfection of mathematics. It's all as simple as 1 + 1 = 2. And in case you don't believe it, I've written up the proof here for you to examine. I hope I haven't introduced any bugs in the proof. We just say that 1 is the successor of 0, the number that follows after 0 in the usual order. And then we need to use the definition of addition, which justifies the second line in the proof. Then we need to know that 1 + 0 is equal to 1 for the next line of the proof, which is again part of the definition of addition. And then finally, that the successor of 1 is 2. So philosophers have, centuries ago, philosophers advanced the argument that math gives us examples of analytic truths that are not capable of being falsified in the usual empirical way, and examples such as the proof of 1 + 1 = 2 are used by them as evidence. So one other difference, I would say, between math and computer science is that I just said that testers in computer science don't even want to correct some of the errors. By contrast, mathematicians can be devastated by even a small flaw in their work. In fact, just this weekend, a friend of mine finally confessed to me, we were graduate students together after 20 years, that there was an error in her thesis that was found after she graduated, and that she had to spend the greater part of a year in trying to correct this. And there are many other examples of mathematicians who, when they find an error in their work, are quite devastated. So let's look at something that's a little more complicated than the proof of 1 + 1 = 2. I brought a book with me today. This is by Fred Omgren, who is a professor at Princeton University. This whole book is giving the proof of a single theorem in mathematics. The original manuscript was 1,728 pages long. He worked on it for 13 years, starting in the 1970s. It wasn't published until, this was published finally in the year 2000. So, question. How do we know there are no errors in this book? So I thought tonight we could go through the proof. Here's page 283. Going backwards, page 282. So it's a bad copy. Let me see if I can bring up something you can look at more closely here. I want to give you a chance to study the proof. Okay, so we have 1,728 pages of this. Why would somebody believe that this proof is correct? So nothing I say today, I don't want to cast any doubts on Fred Armgren's proof that are undeserved, but at the same time, we have a serious question of how we would verify this. I think if I were to spend, I would be very lucky to maybe check a few pages a day. If I could verify 5 pages a day, I'd be very happy. If I could go through the entire proof in a year, that would be great. So are we asking every mathematician who uses this result to go spend a year or two of their lives checking that there are no mistakes in the proof? So for correctness in mathematics, Euclid is our role model. And unfortunately, the first mistake in Euclid occurs in the very first proposition when he proves, so this is a direct quote from Euclid, that on a given finite straight line to construct an equilateral triangle. This is his first proposition. So I've drawn a picture here of an equilateral triangle, and the construction is to use a straight edge and compass to actually make this. And there are assumptions in this proof that don't follow from the stated assumptions about when you have two circles and that they will always intersect if each passes through the other's center. And okay, so Euclid made a mistake. One of my favorite books, The Captive Mind, has this statement as the epigraph. An old Jew of Galicia once said, "When somebody is 55% right, that's very good and there's no use wrangling. And if somebody is 60% right, that's wonderful and it's great luck and let them thank God. But what's to be said about 75% right? Wise people say this is suspicious. Well, what about 100% right? Whoever says he's 100% right is a fanatic, a thug, and the worst kind of rascal." So in the next part of this talk, I want to take a few real-world examples of proofs. The first two are problems that I've worked closely with, and then I've picked the third example, the four-color theorem, just because it's a famous problem in mathematics. So I'll start with the problem of 13 spheres. This is a problem that goes all the way back to Isaac Newton. He had a discussion with the astronomer Gregory, and they asked the following question. I think you can see here that I have one red sphere in the center, and in their discussion they wanted to answer the question of how many other spheres they could put around this one in the middle so that they all touch the one in the center, but these balls can't overlap. And what we have here is an arrangement where, well, I haven't shown all 12, but you can see that there's a ring of 6 here, and then I've put 2 on top here, and there's a room right here to add a third, so you get 3 on top, and then you can do the symmetrical thing on the other side to get 3 more on the bottom. So this is an arrangement with 12 spheres that all touch the one in the middle. And the discussion between Newton and Gregory was whether you might be able to do better than this and find some other arrangement where 13 were actually touching the one in the center. So the first proofs did not appear in the mathematical literature until the 19th century. And then there were 3 proofs that I'm aware of appearing in the 1950s, including a rather famous one by the mathematician Leach. So let's take a look at these proofs. So the proofs are proving that Newton was right and that Gregory was wrong, and that is that it's possible to get 12 to touch, but that it's impossible to get 13 to touch. So when I talk about proofs, I'm talking about this statement that 12 is the maximum possible. So in preparation for an article I wrote several years ago, I went back and read these old papers from the 1870s and found that all three of the proofs were incorrect. So one of them actually didn't even try to give a proof. It was just showing some arrangements, and it wasn't a serious attempt. But one of them was a really serious attempt, but I came up with a very concrete example showing that this proof does not work. And then one of the proofs from 1952 is wrong. But fortunately, this proof by Leach is very elegant and made it into what's called proofs from the book. So the mathematician Erdős had this concept of proofs from the book, and these are mathematical proofs that are so perfect that there's no possible way to make any improvement, and these are proofs that will stand just as they are from now throughout the centuries. So one of Leach's proof made it in as chapter 12, quite appropriately. Now I want to quote one sentence from the book, Proofs from the Book. And this sentence says, if two side lengths stay the same and the third one increases, then the area of a triangle increases. So I've drawn a picture of it here, that we have three side lengths, and then I've increased the side here on the left, and it makes a triangle a bigger area. But now I'm going to keep the same statement and draw a second picture, again illustrating the same statement, but just showing how wrong this statement is in proofs from the book. So this is a serious mistake in this write-up of Leach's proof. How was this dealt with in the second edition? Well, they removed the chapter. So you'll no longer find Leach's proof in proofs from the book. So I want to show you now a picture of 13 spheres, all touching one in the center. So here, it's a little bit fuzzy, but you can make out that on top, there's one on top, and then I have a ring of 4 going around, and then a second ring around the waist going around, and then a bottom layer of 4 going around. So I have one on the top and then 3 rings of 4 for a total of 13 spheres. Now, of course, this is what people for hundreds of years have been proving to be impossible. And I've made models of this arrangement of 13 spheres, one with wood, another with styrofoam, and then a computer graphic. Of course, Newton really was right. This model doesn't exist. When I take the wood model and shake it, I can hear the ball inside rattling. So it's not really touching the others. And the same with the computer graphic. It was fuzzy, but it was fuzzy for a reason. And that is, if you put it in focus, you see that it isn't a real configuration. And the styrofoam, when you make that model, you have to crush the styrofoam to make it work. Okay, so second example. The Jordan curve theorem. Let me say what that is. So the Jordan curve theorem says that if I take a pencil on a sheet of paper and trace out a curve without crossing back over and ending back where I started, that I get a closed loop that divides the surface, the plane, into an inside and an outside. Now, most people, when they hear this statement, think it's so obvious that they can't imagine a mathematician would even waste their time trying to prove that something like this is true. So before I go into the proofs of the Jordan curve theorem, I want to just take a minute to try to raise some doubt about the truth of this statement. So I want to start with an ink block test. So stare at this for a moment and see what images come to mind. What I claim is that I see in here a curve not just from the outline, but I have drawn a curve with a pencil on a sheet of paper without lifting it off the surface in such a way that I filled in the entire red square. Do you see it? Okay, so here again, I have a picture of it in my presentation here, but the graphics weren't good enough, so I've got to go outside my presentation here for a moment to try to bring up a picture of it. Sorry. I don't think I'm going to get it, so let me... Okay, so this is the graphic, but it didn't turn out very well because for some reason the PDF dropped some of the edges. So this should have been a three-sided edge. So I'll just ask you to imagine. And then I repeat it. It looks like a deer's antler. So if these three lines are the head, then I just add some antlers to the head and go around like this. Again, the PDF dropped out some of the edges, so you need to imagine them. And then I just keep repeating that at a finer and finer grid. And it's dropped out some of the edges, so you can't tell that I can trace out this whole thing without lifting the pencil from the page. But I keep doing this at a finer and finer level, and eventually I get a curve that fills out the solid square without lifting the pencil from the sheet of paper. And so you could easily imagine that there might be some sort of Jordan curve that is so intricate that it fills in its own interior. Okay, let me show you a graphic designer's attempt to defeat the Jordan curve theorem. When we have a simple closed curve, it should have a single interior and a single exterior. And here's a picture of two snakes, each trying to be the interior of the region defined by the boundary. We've got the white snake here on the inside and the black snake on the outside, each trying to be the interior. Let me show you my 11-year-old. When I was 11 years old, I liked to make mazes. And here's my attempt to defeat things. I would make mazes that everybody would think would be impossible. But then, if you zoom in at the very bottom here, and let me pull this up in a graphics program, you see that it really is possible to complete the maze because of a little passageway that you don't see unless your vision is really good. So maybe Jordan curves are like this, that they really look solid and that they divide things into an interior and exterior. But if you look at it under a microscope or something, it's possible to get from one side of the curve to the other without actually crossing. And maybe it's something along the lines, say, of Rutherford's famous gold foil experiment, where he shot a beam of alpha particles at a thin sheet of gold foil, and 98% of the alpha particles went straight through without deflection. Maybe Jordan curves are really porous in the same way that physical objects are. So what is the opinion of Jordan's proof? I'll read you a commentary here. Strangely enough, the proof given by Jordan was neither short nor simple, and the surprise was even greater when it turned out that Jordan's proof was invalid and that considerable effort was necessary to fill the gaps in his reasoning. This comes from What is Mathematics, Cron and Robbins, which has been called a work of high perfection and a book of extraordinary perfection, saying that Jordan's proof was incorrect. From another web page, I found the statement. This is the website of a mathematician at a major university. Jordan found that proving this theorem is by no means easy, and in fact the proof that he gave in his textbook is completely wrong. So today mathematicians are in almost complete agreement that Jordan's original proof was wrong. Not everybody, however, is in agreement. I've been able to find two mathematicians in the world who come to Jordan's support and say that his proof was correct. One of them is me. Why do I believe the proof? Well, I've read it, and I didn't find any mistakes. I've studied several other proofs of the Jordan curve theorem in great detail, and it's really not that different from many of the proofs that the other proofs that you find. And I can't find any written record over the past century containing any record of what it was that Jordan really did wrong. So I started writing email to people who say that Jordan was wrong. I wrote to the guy who has the website saying Jordan was completely wrong. And he writes back, I must confess that I haven't more than glanced at Jordan's cours d'analyse. My French is rather rudimentary. I was relying on n-hand sources with n greater than 1. I was also under the impression that the mathematical infrastructure for dealing with such questions is not in place at the time. Another one wrote back, I don't remember my source for that. Another one has written, Jordan's proof is essentially correct, and with some polishing, the proof would become impeccable. This is the other mathematician who supports. Now, I'm not 100% certain that I'm right and the rest of the world is wrong. Maybe some of you can tell me after the lecture exactly what Jordan's proof is, but or what the problem is. But this is an experience that happens and plays itself over and over again in the career of any mathematician. You spend a lot of time trying to check the correctness of other people's results. Sometimes you believe what they have to say, and other times you think you find mistakes, but it's never an easy process to come to the conclusions about the truth of many difficult theorems. I'm sorry. So I just ask, isn't it odd that mathematicians can still be in disagreement about a proof written in 1893? And then, are errors in mathematical proofs really all that different from bugs in computer programs? I mean, we like to think that mathematics is free of all imperfection, but when we ask for real-world examples, we often come up short. So the last one I want to mention is the four-color theorem. This is a very famous old problem that says if you take any map, you can color it in with four colors in such a way that the countries next to each other are not colored in the same way. This question goes back to 1852. The first published proof was presented in the 1880s by the mathematician Kemp. He was honored for his proof by election as a Fellow of the Royal Society. He later went on to be the Treasurer and Vice President of the Royal Society, honored for his work. Now, of course, the picture that I've shown on the right is the example showing that Kemp's proof was wrong. This proof was found to be incorrect by Hewood after about 10 years. So the second proof that was presented was that of Appel and Hawken in 1976. This proof made extensive use of computers, and because of that, mathematicians have been arguing about it ever since. So now I want to turn to the final topic, and that is formal proofs, where we bring computers and mathematics together. Let me try to explain what a formal proof is. In a formal proof, you program the computer to check every single step of a proof, and it doesn't accept anything, nothing whatsoever, until every single last detail has been checked all the way back to the basic logical inferences of mathematics and the basic axioms. People would like to be able to do this by hand. It would, many people would find it more convincing that way. The problem is that when you write out every single step, it becomes much too long to do by hand, and you really have to turn to a computer to carry out all of the details. So to ease us into this, I want to give everybody a quiz on the complexity of bringing everything back to the fundamentals of logic. So if you'd close your notebooks and put your books on the floor, I have the following question for everybody. How many symbols does it take to express the number 1? So I'm just taking the number 1, and I want to expand it out so that I'm not using any definitions or just conventions of language or abuses of notation. I just want to write 1 in terms of the basic symbols of logic. And to make things definite, I'm going to use Bourbaki's theory of sets. So I'm going to make this multiple choice. So everybody who thinks that it's at least 1, raise your hand. I want every hand to go up. Okay? Now, as we go down the list, you can drop out at any time, and eventually all the hands will go down. So if you think that it's at least 10, keep your hands up. If you think that it's at least 100, keep your hands up. 1,000, those that think that it's at least 10,000. So I didn't know when people would drop out, so just in case, I kept going. So at least 100,000. Okay, we're still there. 1 million? 10 million? 100 million? Billion? 10 billion? Trillion? Looks like I'm the only hand up, and I know the answer. The answer is about 4 trillion symbols to express the 1. So somebody actually did the calculation, a guy named Matthias. The definition is highly recursive, and it gets extremely complex. So I think it's true to say that most mathematicians vastly underestimate the gulf that separates mathematics as it's traditionally written and mathematics at the level of the axioms and basic rules of inference. Now, for a computer, something as inefficient as this particular system would never be practical even by computer. So to make things formal, people have devised special systems of axioms that are equivalent to what we use, but are much more efficient from a computational point of view so that you can actually make progress on some of these problems. So I use a particular program that's called HOLITE. HOL is just an acronym for higher order logic, so it doesn't really matter what it means, but this is a computer program that steps through every single logical step in a proof, and there are no shortcuts, no approximations, no hand waving. Every time there are several cases, you have to do every case. It just won't let you go ahead unless it's checked every single last thing. The beautiful thing about this program is that it's written in such a way that it becomes self-checking after the first 1,000 lines of the computer code. So, of course, when you're programming this thing, I said at the beginning of the lecture how easy it is to make bugs and introduce bugs. And if you had a bug in this program, it would be disastrous because then it would be checking something that, well, it'd be checking things in the wrong way, and it might let in things that it shouldn't. So it's self-checking after 1,000 lines of code. So if you can get these 1,000 lines of code that state what the axioms of mathematics, if you can state those correctly and what the rules of inference are, then it's a reliable program. And, well, I said how many bugs there were in an average piece of software, but in highly reliable computer software, you can get rates of reliability of less than 1 bug per, say, 10,000 lines of code. Things that are, extremely important, like space shuttle software. So the question is, do we hope that we can make these 1,000 lines of code in this program bug-free so that we can really check mathematics in a reliable way? So there are no bugs found in the first 7 years this program was used. I found the first bug in July of 2003. Since then, 2 other bugs have been found, all of a similar nature. But I believe that these 1,000 lines of code are among the most, well, they're extremely important lines, I think, for the foundation of mathematics. And I think with time, all the bugs can be found and removed. Of course, you're never sure if there isn't, is there another bug lurking in there someplace that we won't find for another 50 years. But I find that it's some of the most beautifully crafted code I've ever seen. The author, John Harrison, who's now at Intel, is one of the most reliable people that I've met. I feel that eventually this code can get to the point where we can put a large degree of trust, and that it will be able to reliably check every step of mathematical proofs. So nobody knows what percentage of math papers have serious errors. I talk to people, some people say 5%, 10%, some people give higher numbers. I think it would be very difficult to get a precise value on this number just because it's so difficult to check mathematical papers for errors in the first place. So even if computers have bugs, I think they're capable of bringing the error rates in math papers much lower than 5 or 10% if we successfully get this piece of this 1,000 lines of code working that checks these other programs. And I gave these 3 problems as examples in this lecture. I gave the example of the problem of 13 spheres. I gave the problem of the Jordan curve theorem. And I gave the example of the 4-color theorem. So I've implemented one of these already in this package, the Jordan curve theorem. So I've stepped through every single logical step of the Jordan curve theorem inside this system. And of course, you start out with a rather short proof, and by the time you expand everything out, it becomes much longer. In this case, it ended up about 60,000 instructions in the proof to see how this all goes. I'll answer questions in a few minutes. And then somebody else, Georges Gontier, that I quoted early in the lecture, he has done the 4-color theorem this way, which is really an amazing accomplishment because the original proof relied on long computer calculations, and he's successfully moved all of those long computer calculations and all of the results about graph theory that you need into one of these systems, and it is stepped through every single step of the proof. And this at least to me, makes the 4-color theorem much more believable and reliable than, far more so than ever in the past. It's really an amazing accomplishment. And then, well, I have plans to do the 3rd of these problems that I mentioned, this problem of 13 spheres, but that hasn't been done yet. I've just done some preliminary work on it. So the hope is that even though computers are unreliable, they can be more reliable than some of the mathematicians writing papers today, and that these tools of formal checking will be very useful to mathematicians. In the introduction, so the Keller conjecture about sphere packings was mentioned. I have a long-term research project of trying to check that proof, showing that a certain packing of spheres is the best possible inside one of these systems. I estimate right now that it may take up to 20 years of work to put that one theorem into the computer. Fortunately, there are several others who have become involved in the project, and if you have 5 graduate students spending 4 years to write a dissertation, you have 20 years right there. So perhaps this will actually be done before I die. But so thank you very much. Yes.
So I have a question regarding this checking by computer. You said that you even need trillions of symbols to define the number 1. So why is it that you can do that computer checking? I assume that the number 1 will probably occur in that.
Yes. Yes. Certainly. So the quiz was for a specific system of axioms, the Bourbaki's theory of sets. There are different ways to set up the foundations of mathematics. One was this one done by Bourbaki. There's a standard Zermelo-Frankel system of axioms. So you get to choose which system you use, and people chose one other than the Bourbaki system for exactly this reason, because it would not have worked very well on computer.
What are the implications of Gödel's incompleteness theorem for this work?
Well, so people would like to write just a long computer program that would automatically generate all proofs of all true statements, and of course you can't do that. People are putting in, so in the days before Gödel, people were trying to prove decision procedures, and they were successful in proving certain decision procedures. There's one for additive theory of arithmetic, there's one for real numbers, and these decision procedures that work in limited contexts are being put into these systems, but of course there's no hope for something universal because of Gödel's results.
Are there any other questions? Okay, before you go, I wanted to remind you that this lecture is brought to you by the Institute for Mathematics and its Applications, which is an interdisciplinary math research institute here on campus that brings 1,000 mathematicians and scientists here every year to the U, and also with the support of the IT Alumni Association. On the table on that side of the room, those of you who want a certificate of attendance, for example, to show your teacher, there are some there. And the IT Alumni Association also has some of their brochures. And I want you to remind you to keep an eye out for our poster of next year's Math Matters series. And again, to thank Professor Hales.